There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. Isn't that interesting? I hope you're all paying attention. There's going to be a short quiz later on. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, redenzine, and zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Becoming grapes with...
In this video, we're illustrating osmosis using raisins.
Yeah, the raisins...
The raisins are in hot, plain tap water.
And wouldn't they be becoming grapes? Because raisins are the dried up grapes. So.
And this is plumping them up, so it's kind of restoring them to becoming grapes.
The prune is becoming a plum.
Yeah, in this video we have a prune, which is a dried up plum, in hot tap water. And over time it plumps up.
We're using osmosis.
Through osmosis, as the water goes from outside the prune, where it has a high concentration, to inside the prune, where it has a low concentration.
Okay. I was eating an apricot.
Okay, in this clip, we're looking at a dried apricot in warm water using time-lapse photography. It's speeded up by a factor of 512, like the other one. And in the next clip, the dried prune is placed in
the dried apricot. It's a dried cot.
Okay, in this clip, we place a dried apricot in warm, sugary water, very concentrated water, and you see that it doesn't plump up because the concentration of the water on the outside is diluted.
And there's less concentration.
Okay, in this video, we are looking at the diffusion of yellow dye and a blue dye. The bottom solution shown has yellow dye in a saturated salt solution, and I pour on top of that a blue dye with just in plain water. And although there's a little mixing in the beginning, we see green and yellow rather than blue and yellow. Once it reaches the little bit of mixing that it has, it stays pretty constant. And this video was done over a period of almost a full day, and yet we see very little change aside from the initial mixing. And that's because when you
diffusion is slow.
Do diffusion in liquid solution, it's very slow.
Diffusion is slow.
Now, sometimes it doesn't seem slow because there are other things going on, such as convection currents.
Like undiffusion.
Okay. But when you do it right, it's very slow. Now, in contrast, diffusion in gases is much faster, but the reason for that is the molecules are far apart and they're able to move around quite quickly. And just imagine you were in a crowded room, like that's a metaphor for a liquid, and you're trying to get from one side to the other, and there's people.
It's going to take a long time, like a day.
It's going to take a long time to get from one side to the other. Okay.
Even weeks.
Okay, so we'll do some more diffusion experiments in the future, but I think this nicely illustrates that diffusion in liquid solution is fairly slow. But you have to be careful to do it right. All right.
Yeah, you need
It might
to do
seem
it right.
fast, but then you're getting a lot of convection currents.
Yeah, do it right. Yeah, you need to do it right. If you don't do it right, then diffusion could be even more slow than slow. And we're already diffusion slower than slow. It's diffusion!